In computer science, random access machine is an abstract machine in the general class of register machines. The RAM is very similar to the counter machine but with the added capability of indirect addressing of its registers. Like the counter machine, the RAM has its instructions in the finite state portion of the machine. The RAM's equivalent of the universal Turing machine, with its program in the registers as well as its data, is called the random access stored program machine, or RASP. It is an example of the so-called von Neumann architecture and is closest to the common notion of computer. Together with the Turing machine and counter machine models, the RAM and RASP models are used for computational complexity analysis. Van EMDE Boas calls these 3 plus the pointer machine, sequential machine models, to distinguish them from parallel random access machine models. Introduction to the model. The concept of a random access machine starts with the simplest model of all, the so-called counter machine model. 2 additions move it away from the counter machine, however. The first enhances the machine with the convenience of indirect addressing. The second moves the model toward the more conventional accumulator-based computer with the addition of one or more auxiliary registers, the most common of which is called the accumulator. Formal definition: a random access machine is an abstract computational machine model identical to a multiple register counter machine with the addition of indirect addressing, at the discretion of an instruction from its finite state machines table. The machine derives her target register's address either directly from the instruction itself, or indirectly from the contents of the pointer register specified in the instruction. By definition, a register is a location with both an address and a content, a single natural number. For precision, we will use the quasi-formal symbolism from Boulos-Burgess Jeffrey to specify a register, its contents, and an operation on a register. R means the contents of register with address R. The label R here is a variable that can be filled with a natural number or a letter or a name. Means copy, deposit into, or replaces, but without destruction of the source. Example: 3 plus 1 3 means the contents of source register with address 3 plus 1 is put into destination register with address 3. If 3 equals 37, that is, the contents of register 3 is the number 37, then 37 plus 1 equals 38 will be put into register 3. Example: 3 5 means the contents of source register with address 3 is put into destination register with address 5. If 3 equals 38, that is, the contents of register 3 is the number 38, then this number will be put into register 5. The contents of register 3 are not disturbed by this operation, so 3 continues to be 38, now the same as 5. Definition: a direct instruction is one that specifies in the instruction itself the address of the source or destination register whose contents will be the subject of the instruction. Definition: an indirect instruction is one that specifies in pointer register, the contents of which is the address of a target register. The target register can be either a source or a destination. A register can address itself indirectly. For want of a standard convention, this article will specify direct, indirect, abbreviated as DI, as a parameter in the instruction. Example: copy means directly get the source register's address from the instruction itself, but indirectly I get the destination address from pointer register n. Suppose n equals 3, then register 3 is the destination, and the instruction will do the following. 3. Definition: the contents of source register is used by the instruction. The source register's address can be specified either directly by the instruction, or indirectly by the pointer register specified by the instruction. Definition: the contents of the pointer register is the address of the target register. Definition: the contents of the pointer register points to the target register. The target may be either a source or a destination register. Definition: The destination register is where the instruction deposits its result. The source register's address can be specified either directly by the instruction, or indirectly by the pointer register specified by the instruction. The source and destination registers can be one refresher. The counter machine model Melzack provides an easy visualization of a counter machine. Its registers are holes in the ground, and these holes hold pebbles. Per an instruction, into and out of these holes, the computer adds or removes a single pebble. As needed, additional pebbles come from, and excess pebbles go back into, an infinite supply. If the hole is too small to accommodate the pebbles, the computer digs the hole bigger. Minsky and Hopcroft-Ullman 1979 offer the visualization of a multi-tape Turing machine with as many left-ended tapes as registers. Each tape's length is unbounded to the right, and every square is blank except for the left end, which is marked. The distance of a tape's head from its left end, measured in numbers of tape squares, represents the natural number in the register. To decrement the count of squares the tape head moves left, increment it moves right. There is no need to print or erase marks on the tape. The only conditional instructions are to check to see if the head is at the left end by testing a left-end mark with a jump if marked instruction. The following instruction, mnemonics, e.g., CLR, are arbitrary. No standard exists. The register machine has, for a memory external to its finite state machine, an unbounded collection of discrete and uniquely labeled locations with unbounded capacity, called registers. These registers hold only natural numbers. Per a list of sequential instructions in the finite state machines table, a few types of primitive operations operate on the contents of these registers. Finally, a conditional expression in the form of an if-then-else is available to test the contents of one or two registers and jump the finite state machine out of the default instruction sequence. Base model 1. The model closest to Minsky's visualization and to Lambic. Increment contents of register R, decrement contents of register R. If contents of register R is 0, then jump to instruction is else continue to next instruction. Base model 2. The successor model. Increment the contents of register R, clear the contents of register R. If contents of register Rj equals the contents of register Rk, then jump to instruction is else go to next instruction. Base model 3. Used by Elgott Robinson in their investigation of bounded and unbounded rasps. The successor model with copy in the place of clear. Increment the contents of register R, copy the contents of register Rj to register Rk. If contents of register Rj equals the contents of register Rk, then jump to instruction is else go to next instruction. Creating convenience instructions from the base set. The three base sets 1, 2, or 3 above are equivalent in the sense that one can create the instructions of one set using the instructions of another set. Declare a reserved register, e.g., call it 0 to contain a number 0. The choice of model will depend on which an author finds easiest to use in a demonstration, or a proof, etc. Moreover, from base sets 1, 2, or 3 we can create any of the primitive recursive functions. Boulos, Burgess, Jeffrey. However, building the primitive recursive functions is difficult, because the instruction sets are so primitive. One solution is to expand a particular set with convenience instructions from another set. These will not be subroutines in the conventional sense, but rather blocks of instructions created from the base set and given a mnemonic. In a formal sense, to use these blocks we need to either expand them into their base instruction equivalents, they will require the use of temporary or auxiliary registers, so the model must take this into account, or design our machines models with the instructions built in. Example: base set 1. To create CLR, use the block of instructions to count down register R to 0. Observe the use of the hint mentioned above. CLR equals equivalent loop JZ dec JZ exit etc. Again, all of this is for convenience only, none of this increases the model's intrinsic power. For example, the most expanded set would include each unique instruction from the 3 sets, plus unconditional jump JIE, CLR, DEC, INC, CPY, JZ, JA, J. Most authors pick one or the other of the conditional jumps, e.g., Shepherds and Sturgis use the above set minus SHA.